Okay, so we're very pleased to have, well, George's Obied and Cumrun Vafa, or Cumrun Vafa and George's Obied, and they're going to tell us about topological gravity as the early phase of our universe. Okay.
Very good. Thank you. Thank you so much for the invitation. George and I are glad to give this talk here. George is my student, and also just to make a point, he's finishing his PhD this year, so keep an eye on him. So we're going to talk about topological gravity as the early phase of our universe, and this is a work we have done with Georges and Pratik Agrawal and Sergei Gukov in a paper which appeared last month. So the outline for our talk is we first review the dualities that motivate this scenario. We then talk about puzzles of early cosmology. Then we talk about the topological scenario that we are going to propose. This is going to be the first half that I will describe. And then the second half is what Georges will talk about, which is starts with Witten's topological gravity, and then phenomenology of our model, and the analogy of our model with QCD. So that's the outline for our talk. So dualities are ubiquitous in string theory, and they're everywhere. And that was one of the major discoveries, of course, of string theory in the past few decades, is understanding various kinds of duality. And it's essential to take them into account precisely when we take extreme limits of parameters in the theory. Whenever you have extreme limits, you have dualities of some kind. In other words, if you start with any given effective theory in some region of parameter space, when you take the extreme regions, extreme limits of parameters in your theory, you find that your theory breaks down, and new light modes will appear in these extreme limits. The new light modes are the ingredients which describe the dual to the theory that we are interested in. So the description breaks down, and a new dual description takes over when you go to the extreme parameters. This is one of the basic, I would say, probably the most important discovery we have made in string theory in the past few decades, is just this fact. Of course, there are different limits we can take and different kinds of things, but always, always, when we take extreme limits, we find a dual description. So in fact, this is captured by what we call the distance conjecture. The distance conjecture is exactly that statement, that if you start with a space of parameters, which is moduli space we call, and this could be like expectation value of some scalar fields that describe your theory and so forth. When you go to extreme regions of this, if you go to far and far distances in parameter space, you find that there are these regions where you can go to infinitely far away distances. But whenever you go to these distances, you find that there's a tower of light states that emerge. And their tower of light states have masses which go exponentially down with the distance of this, with distance you traverse in this scalar field web. So that is the distance conjecture, and it is everywhere in string theory. Okay, so this is the basics backdrop of where we want to basically start asking the question in the context of cosmology. So what is early universe cosmology in particular is what we are going to be focusing on today. And the early universe cosmology is an extreme limit. It is extreme because we have two limits we have to take. Well, they are correlated, of course. We take the radius of the universe going down, shrinking and shrinking towards zero, and the temperature, therefore, begins to go higher and higher towards infinity. Of course, you never go to zero and you never go exactly to infinity, but this is the direction you're heading. Therefore, this by definition is an extreme limit of the parameter space, and therefore we should expect that our description breaks down. We cannot expect that the standard model coupled to Einstein gravity describes the region where the temperature is going to infinity or the radius is going to zero. So why is that? Well, if you, for example, take the temperature can be viewed in the Euclidean time circle as being related to the inverse of the Euclidean time circle parameter. And so the radius is beta over 2 pi. And the distance relevant for the distance conjecture it turns out because the radius, when you compute the metric in the distance space, goes like log r, and therefore you get a parameter which goes like log beta in the distance. So therefore, as you go to the ever so larger t, which means as you go to ever smaller radii or ever smaller beta, you see that you're going to get an infinite distance away, and you get masses which scale like some power of in this distance times some constant. But e to the log beta is related to temperature, and therefore you're just going to get a factor of t to the minus b. In other words, as the temperature goes to infinity, you get the tower of light states which go to 0. And therefore, our description must break down as temperature goes to infinity. Regardless of how it's breaking down, we expect it to break down. Similarly, as the radius goes to 0, we expect the description to break down just for the same reason as if you think about it, for example, in a toroidal setup, if you think about this as the radius, again, the same fact will imply that you get the tower of light states. So distance conjecture predicts that we should get a tower of states, and in fact, we can predict how they scale these masses with the temperature. This is the relation. So we expect to have such light states, and therefore we better accommodate this. So our description must be breaking down, and so some new description should take over. So let's now shift gears and talk about observational cosmology and what are these puzzles of early cosmology that we are trying to explain in our model. And if you look at the puzzles of early cosmology, many of them are the statements of the type of vanishing, like why something is vanishing. That's basically turns out to be a typical statement. So for example, horizon problem is related to homogeneity. Is why is the universe homogeneous? Why is the gradient of density or temperature or whatnot, why doesn't it depend on positions so much? Why is it almost 0? Or flatness is why when you go around the loops in space, why you come back to yourself with no rotation? Why are we having really a flat background? And the fluctuations, well, it's not exactly homogeneous. It's slightly, there's some slight fluctuations. And so the question is, what is these density fluctuations? Why is the amplitude for these density fluctuations, the 2-point function, is scale invariant, and it almost does not depend on the x and y. Well, it's almost scale invariant, but there's a tiny power. So why is it that we're getting such a small dependence on positions? So in other words, it's almost like x minus y to the 0, there 0 dx is 0, and the idj is 0. So in some sense, it is telling us that you don't see positions. Things having to do with spatial positions or actual positions somehow does not show up in early cosmology. It's independent of it, unlike a lot of physics that we do know and should depend on it. And this is related to a lot of the puzzles of the early cosmology. So what are some of the popular approaches to this problem? Well, the most prominent one and the one which has been studied most is inflation. And as you all know about it, so I won't describe it too much. And similarly for the bounce models is another example that people have studied. But the main point is that in both of these approaches, what you have is that you include additional terms in the same effective Lagrangian. So the Lagrangian does not break down. You just have extra terms in your Lagrangian, and that describes your theory. In the case of inflation, you have an inflaton with a potential, and similarly with higher derivative terms in the bounce models, you have some other terms. So you have some kind of corrections to the action, but not infinitely many terms. So when I say that the effective field theory breaks down, I don't mean that you just have to get one or two more terms added or a few more fields added to the Lagrangian. When I say that the effective field theory in the distance conjecture, in the string theory, when I say that breaks down, it means that you need infinitely many fields to change the theory, to describe the theory, which means that you basically have to give up the description that you started with, unlike inflation or bounce models. So the framework and the basic paradigm of these models is trying to find a scenario, a formulation of the Lagrangian, which can describe the whole theory in one framework. Whereas in string theory, we don't expect it to be the case. In fact, there are these difficulties related to these scenarios, and in particular for inflation, where some of the swampland conditions, such as difficulty in getting the flattened potential, come in the way, so it makes these models also unnatural from that viewpoint. A natural resolution to these problems, and that's the approach that we would like to take, is if the early phase of the universe is a topological theory. A topological theory is a theory whose correlation functions do not depend on positions. This is a generic feature of a topological theory, that if you take correlators of topological observables, you just get some numbers which depend on the indices of what operators you're putting, but does not depend on the positions of where you insert them. In other words, you get the derivative of these correlations with x's vanish. This has the flavor of early universe cosmology puzzles that we had. In other words, the choice of the metric in the in this setup, in the topological field theory, does not matter. It does not depend on distances anymore. Such quantum field theories have been studied and originally proposed by Witten in realizing Donaldson theory in the physical context. But is it natural to have this from the perspective of string theory? That's the question.
I have a question.
Yes?
So here the xi, the coordinate include time as well, right?
That's correct.
But do we have any observational evidence for the early universe that, I mean, the observation is independent of time as well? It's only spatial direction, no?
That's correct. So there's going to be something which happens that breaks the time symmetry. There should be, and I will explain that. Okay. So here we are starting with something which is space-time invariant. But of course, the background could be different. So what I'm writing here, so let me explain more precisely what I'm saying. This is the expectation value in the vacuum of the theory. So the vacuum of the theory would be this. But of course, you could have a background, in which case you would have some things that you have. And in fact, as we'll explain, in our case, there'll be a background which is time dependent, but not spatially dependent.
Thank you.
So such quantum field theories have been studied in the context of many examples that originated with the work of Witten and, for example, Donaldson theory and others, a context that they have been used. But is it natural from the perspective of string theory? That's the question. So to see why it's actually natural from the perspective of string theory, it is useful to remember the string gas cosmology, which is one of the motivations for this picture that we're going to advocate. This is a model that was studied a while back with Brandenberger and also studied further with Witten, and many other people studied it. And the motivation for this string gas cosmology was the fact that basically was string dualities, that if you take the box of the universe to be in a periodic box, like a three-dimensional torus, and if you have, for example, let's say heterotic string, it has T-duality. That is, it has an inversion symmetry for L to 1 over L. In other words, if you look at the moment, if you look at the a box of a universe of size L, there will be various string excitations in it, and they will be moving around with momenta, which is quantized in units of 1 over L. And they could also be winding around the various sides of this universe, whose energy are proportional to the winding number times the length of the box. And this theory for heterotic strings has this duality symmetry that if you change L to 1 over L, it is equivalent to exchanging the momentum and the winding modes. The N and M get exchanged. Now, this actually points to the issue that we don't, which is very unique to string theory, is that the notion of the position is not duality invariant. You see, you can define the notion of position as usually we do in terms of Fourier transform of momentum variables. But now you can use the windings as a new way to define a new position, x tilde. So you have two different notions of positions, x and x tilde, Fourier transform to be of momentum modes and the winding modes. Under L to 1 over L, they exchange their roles. So in other words, if the universe is big in terms of x variable, it is small in terms of x tilde variable, because that's the L to 1 over L exchange. But if it is small with respect to x, then it's big with respect to x tilde. So x is going to be our variable, the variable that we measure in our universe, and x tilde is going to be the variable that is not natural for our universe. In other words, when the universe is large, when this universe is large, the variables that are relevant are the light modes, and these winding modes are extremely heavy because their energy goes like m times L, so we're going to be decayed out by that time, so we don't have these winding modes, and everything is naturally described in terms of the momentum modes, and therefore the x position is useful. And when L becomes very small, then the opposite happens. These momentum modes become super heavy, but these winding modes become light, and therefore the new variable, which is useful, is the x tilde variable. So you see that the physics that we usually talk about, for example, the description of fluctuations and this and that, is in terms of the x variable. But the early universe, if you come back from small l, its a better variable is not that, it's a new variable, and that's the x tilde variable. And that's the variable we have to have a description for. In other words, if you think about time and temperature as a function of time, so the usual FLRW cosmology, as you grow in time, the temperature goes down, and that's where we have the momentum modes. But when you go back in time, there will be a region where the momentum modes get converted to the winding modes, and as x gets smaller and smaller, then it is the x tilde variable becomes a good variable. And in terms of x tilde, the universe is expanding, even though in terms of x, it's still contracting. So it's in some sense like the bounce, but not quite, because in terms of the x variable, the volume is shrinking, but it behaves as if there was a bounce in terms of a new variable. So the new variable is what is actually taking over, and that's the x tilde variable. And so this is the FLRW of the x tilde universe, whereas this is the FLRW of our universe. So what looks to us as a big crunch is actually a big expansion, or the regular expansion for FLRW of this x tilde variable. This shows the shortcoming of trying to insist that there's a single description of the full universe by our x variables. It just breaks down. We should not be looking to describe the whole universe in terms of the x variables, and that is why we have all these puzzles in cosmology. All these puzzles of cosmology are there because we try to insist there should be a complete description in terms of x variable and the fields which live in the x variable, because we take the viewpoint that our universe is special and it should describe all the time, and at every time it should be the right description. But that's not the case. You have to go to the dual description. So this is what I just said. As we go back in time, momentum mode get converted to the winding modes, and you have to go from one variable x to the x tilde variable. And the better description is going to be in terms of the x tilde variables. And x tilde variable will have its own gravitons. So this graviton of x tilde variable has nothing to do with our gravitons that we describe. So they're dual gravitons, which is completely new degrees of freedom, which just are super heavy in our description when we get to our universe. But now they become light and they take over. So it's a very beautiful description in string theory of how you can have perfectly consistent theory just from this T-duality, which we really understand really well in string theory, which tells you that the early phase of the universe would have to have involve some new degrees of freedom, which we have no access to in terms of our degrees of freedom. So the important difficulty in extracting predictions from string gas cosmology is a better description of the early phase, and that is what was not available before. So because we cannot use the X graviton anymore, and we have to, so the usual picture that we use, for example, for the fluctuations as modes exiting and re-entering horizon in terms of the X variables would not be the right language in the context of this early universe, because X is not the right variable to describe it.
Sorry, Cumrun, what are you assuming about topology here?
I'm not assuming anything for topology, but I'll get to some description of it. Actually, not me, but we'll get to it when Georges talks about his part. We'll see that even though we will not assume something about the topology, about the geometry, we'll get something like flatness and so on. So that will come in. That will come in when Georges talks about it. I'm not assuming compactness or anything like that.
So what sense are you talking about T-duality then?
No, this was just an example. This was, so just to make sure, the string gas cosmology was just a motivation, but we are not going to use string gas cosmology. We're not going to use T-duality. We're not going to use this variable. So now I'm going to basically say what we're going to assume. from here points on. So this is our model. So all of this up to this point was a motivation for what we want to do. Now I'm going to set what is our model. So the principle we believe holds more generally than in T-duality, because as I said, in extreme limits, there's going to be a dual description. What is that dual description? We do not know. It could be winding modes. It could be something else. We do not want to assume what it is. We don't want to box ourselves to some particular description because we don't know. So what are we going to assume? Well, we're going to assume we have two phases and two frames of reference for field theories, which we'll call them 1 and 2. And we talk about operators depending on which mode we are interested in, but we are interested in operators which are relevant for our phase, like fluctuations or density and so on in our universe. So these operators, which they are made of eigenmodes of our modes, they are light in phase 2. So phase 2, I'm going to identify with our universe, and phase 1, which is the original phase of the universe, in that phase, the eigenmodes of these operators will be extremely heavy, like the momentum modes or whatnot. So we start in phase 1, and we have this initial state which is annihilated by non-zero modes of O. So in other words, there's no excitations for these O operators. So O has no excitation whatsoever in phase 1. In other words, the phase of O operators in phase 1 are just zero modes, which means they don't depend on coordinate positions. They are topological. So evolution causes, so if you're interested in describing these operators in the early phase, you better end up with some kind of a topological description. Evolution causes the zero modes to decay almost uniformly to phase 2 matter. So that's our prediction. That is, you're evolving, and the modes which are heavy in the original phase become light, and vice versa. They switch roles, and therefore the matter which was light originally becomes heavy, and they should get converted. So in other words, we have a situation where you have a phase 1 and a phase 2 as a function of time. We say, let's say at time t equal to 0 is where you go from one phase to another. The matter in phase 1 is something we don't know much about, but we are going to be assuming that there's a background in which they just get converted at some time, which we call t equals 0, to the matter that we are made of. And that is the time evolution will bring it to this, that it causes these to be heavy, and so therefore they will decay to the matter in phase 2, and then you're going to have the FLRW taking over. So the matter that we are made of would not exist in the phase 1, and the matter that was in phase 1 would die off as you go to the phase 2. So it's a matter conversion. So if we assume that the matter conversion is just blind to whatever degrees of freedom you have, there's no preference, of course, naturally you get phase 2, which is automatically thermal. In other words, the matter in phase 1 has no information per se, and the only thing we are dealing with is approximate local energy conservation. And so in that form, you're going to get some kind of a thermal background automatically in phase 2, just by this conversion assumption. Now, what we're going to see is that there could be weak non-thermal correlation in phase 2, which emerge from quantum effects of something which actually originates in phase 1. And these look like global or non-local effects from the frame 2 perspective. In other words, we have this background of a thermal created matter here. On top of it, we have fluctuations which have been imprinted due to some quantum effects, as we will see, from phase 1. So therefore, we assume that the different frames have different perspectives. From the perspective of frame 1, which is not our perspective, the original universe is some kind of a radiation-dominated or matter-dominated universe, and by the time it passes time to equal to 0, in frame 2, we get converted to radiation matter in our language. But our universe will only exist in terms of 0 modes in the original phase, and vice versa. The frame 1 matter will only exist in topological sense in phase 2. So in other words, as far as the frame 1 is concerned, that universe has ended except for some topological 0 mode degrees of freedom in our phase. And vice versa, when you go back in time, our degrees of freedom are purely in the topological phase. So,
excuse me.
yes.
So I guess I shouldn't understand your topological gravity as an effective field theory in phase one, right? Because they might couple to these emergent light Taroff modes.
So in the original phase, in the topological phase, that in the frame one, sorry, in the t less than 0, from perspective of frame 2, there's a topological phase.
And is that so is topological gravity an effective quantum field theory?
That's correct, in this phase.
And they don't couple to the light, let's say, winding modes or something?
That's correct, they don't. They are
how do we know that?
Well, because they just have x degrees of freedom. They're just x variables. They can only couple to it as far as being topological. So you just write down what is allowed for topological. And all we know is that our graviton at that phase do not have propagating degrees of freedom because all the modes have been converted. So our gravity better have become topological, whatever it is. So in other words, said differently, they could be some kind of remnants of this radiation mode in terms of anomalies and this and that for the topological phase. And we will see that's actually crucial for us. But that's all. In other words, you can have some imprint on the topological theory as long as it's consistent with topological invariance.
Okay, so you're saying that the coupling is somehow weak or forbidden.
Correct.
Between,
Correct. In other words, there's no phi of x tilde which is coupling to these guys. These are fields are different variables. This just doesn't make sense in our variables. For example, just to give you an idea, this phase as t less than 0 might be a 6-dimensional space. It just doesn't make sense to talk about them. We don't know what space it is. It's a dual description, whatever it is. All we know here is that our description, from our perspective, you only have 0 modes left over. That means that there is no propagating degrees of freedom from our perspective. Some kind of topological phase.
Okay, thank you. Yeah.
Welcome. So what we are going to be doing, so first of all, the horizon problem is automatically solved as I discussed before, but because the matter is just converted to our matter and just they are happening all over the place, the fact that it's non-local, the fact that there's no, the horizon problem is not there is precisely related to the fact that it's non-local physics. In other words, the physics of the frame 1 or phase 1 is non-local relative to our phase. And therefore, there's no surprise that the horizon problem is automatically solved. Not a big deal. What we're going to be considering is we have to know which kind of topological theory we're going to take. And we're going to take, for our example here today, as an example, Witten's 4D topological gravity. We do not know what is this topological phase. So we're going to view this as a model for what it could be. We're not saying it has to be this, but at least we would like to investigate what if it was the 4-dimensional topological gravity that Witten introduced. There are not too many topological gravity models. In fact, this is one of the main ones. And so we might as well study the one which has been proposed a while back by Witten. And now I turn over to Georges, who will talk about that.
See, we just need to get somebody to switch this over for us.
Okay.
Okay, do you see my screen?
Yeah, I think we're okay, right?
Okay. Yeah, so thank you again, and thank you for the chance to speak. And yeah, I'll be taking over from here and discussing Witten's topological gravity. So mainly the second half of this talk, I will just fill in some of the details and give an example of how our topological scenario may be realized. But before we get into that, let me just first give a very brief introduction to the structure of topological theories that we will be using. Okay, so roughly speaking, topological theories are those that don't have local excitations. So these theories do not have local particles in the same way as the standard model, for example, does. The simplest example, which might be familiar, is gravity in 2D. So if you consider a theory of gravity in 2 dimensions, there are no gravitons that propagate in 2 dimensions. And the action itself, it provides a topological invariant. It returns the Euler characteristic. So this Euler characteristic is, of course, position independent. It's just a number, and it measures only global features of the space. For example, the Euler characteristic is just related to the number of handles, the number of boundaries, and the number of crosscaps in the 2-dimensional space. But it's only a measure of global features. And Yeah, so as such, because there are no local excitations in topological theories, usually questions about signal propagation are not good questions to ask. So just like what was said before, the horizon problem, for example, is not necessarily a good question to ask in a topological theory, because one cannot ask how long does it take for a signal to propagate. There are no propagating signals to begin with. Okay. So there are various classes of topological theories, and in here we will deal with one of them. And these are the so-called Witten theories, Witten type theories. These theories have a charge operator Q that's called a BRST operator Q. And this operator is a scalar and is Grassmann odd, so that it maps bosons to fermions and it maps fermions to bosons in a way similar to the supersymmetry operator and to the supercharge and supersymmetric theories. And so in addition, in the Hilbert space, we will identify states that differ by a Q exact contribution. So we will say states alpha and alpha plus Q beta are physically the same. So this type of identification might again be familiar from electromagnetism, where we have a type of gauge invariance. So A is identified with A plus D lambda, and this leads to a similar identification of states in the Hilbert space as well. Now, in electromagnetism, this gauge invariance makes the longitudinal mode of the photon unphysical. And in a similar way, this identification here will make certain local degrees of freedom unphysical. And in fact, in topological theories, all local degrees of freedom will be made unphysical in this way. So in the topological theories that we consider, just like I mentioned, there will be no local degrees of freedom. Okay, so let's now turn to a specific example, which is Witten's four-dimensional topological gravity. And this is an example of a cohomological theory, just like the one I discussed in the previous slide. So in particular, this does contain a BRST operator Q, similar to the one I mentioned on the previous slide. And so in order to construct this theory, Witten starts with tetrad, which carries the degrees of freedom of the metric. And he takes an action for the tetrad that is scale invariant and is based on the Weil tensor, as opposed to an Einstein-Hilbert term. Then to this action, he adds fields called B, C, chi, lambda, and psi. And these fields and the tetrad, they transform into each other under the Q symmetry that we talked about before, so that the full action is invariant under Q. And just in the same way we mentioned, so this topological invariance removes all local degrees of freedom from this action, so that this action does not propagate any local degrees of freedom. So there are a few points worth mentioning here. The first is that this theory is based on W squared, so one might expect it to have ghosts or not be unitary. But because of topological invariance, this is in fact a unitary theory. So it doesn't have negative norm states. It doesn't have any ghosts. And another point worth mentioning is that one cannot generate an Einstein-Hilbert term. So we cannot generate a term in the action that's responsible, that gives back general relativity. For example, if we have another sector that we integrate out, we will not generate a term that gives back general relativity, because this is forbidden due to BRST invariance. So this action is protected by topological symmetry. Okay. So let me now address a few features of the theory that will be important to us later. The first one is, and now we have a theory with the fermionic symmetry, this BRST symmetry, and we can ask what type of background preserves this BRST symmetry. So, and the answer to this turns out to be, again, similar to the answer in supersymmetric theories, namely that the backgrounds that preserve BRST symmetry are those where the variation of fermions is 0. So in Witten's theory, there are 3 fermions, and the one that gives a non-trivial constraint is chi, because the variation of chi is proportional to W, the Weil tensor. So the vanishing of the variation of chi means that backgrounds that preserve BRST invariance have W equals 0. So this condition will be important for us later. The second feature is that this theory has an additional sector. In fact, the simplest action that is topologically invariant does not include kinetic terms for C and psi. And so the action itself is degenerate. And in order to add these kinetic terms, Witten had to introduce a field phi, which belongs to a different sector, non-gravity sector, say a matter sector. And this field phi is there to make sure that the action continues to be scale invariant even after we add these kinetic terms. So adding these kinetic terms without phi would spoil scale invariance. And the only way to fix it is to introduce another field phi. So in essence, this theory has to have some additional sector. In here it's just one field phi, and it's a singlet under the BRST, so it doesn't transform under BRST. Yeah, and it doesn't belong to the gravity sector. It's, for example, it belongs to the matter sector. Okay, so this is a recap. These are the three important aspects of topological gravity that we will need for the rest of the talk. The first one is that the action is based on the Wild tensor squared, and we will add an overall factor, 1 over lambda squared, which will be similar to the coupling in Yang-Mills theories. So this is the first point. The second point is that we saw that that backgrounds that preserve topological invariance have W equals 0. And lastly, that the theory has a BRST invariant massless field, capital Phi. So now that we have this theory, we can ask, what does this mean for cosmology? What cosmology does this theory give us? So let's begin by addressing the flatness problem. So I guess before I start with flatness, so are there any questions? Okay, so
I have a question. Yeah.
Yes.
So before introducing your massless field phi,
yeah,
is it theory just Fadi-Popov gauge fixing action of this Y tensor scale term, or is it more than that?
It's more than Fadi-Popov gauge fixing. It's an additional sector. That's a good question. Yeah.
So what are they? Could you explain?
Yeah, it's more.
What are the additional things?
So this one, it's a BRST singlet, so it's just a completely additional sector. It has nothing to do with.
That I understand, but except phi, phi, all other fields you have BC and chi and psi. They are all part of BRST action. Exactly, not more than that.
Yes, only these are part of the gravity action. So these transform into each other.
These are just usual Fadi-Popov action, yeah.
Yes, so they're ghosts and ghosts of ghosts. Yes, that's correct.
Okay, thank you.
Yep.
Sorry, Georges, where did the small lambda come from?
Small, yeah. We just added an overall lambda to the action. It's just an overall constant because we will use it later. But this doesn't spoil the topological invariance. It's just an overall constant.
Thanks.
And it turns out that as George will explain, that lambda is related to that phi. So you can think about it like a dilaton in a sense. That phi field is not unrelated to lambda, but he's going to say that in a second.
Right. Okay, so now given this action, let's see what this means for cosmology. And first, let's begin with the flatness problem. So in the topological theory, we don't have any observables that distinguish positions or directions. And so the metric that we start with in our phase should be a homogeneous metric. So it's FLRW with k equals -1, 0, or 1, depending on the spatial curvature. However, we saw that in Witten's theory, backgrounds that preserve topological invariance actually have W equals 0, so they're conformally flat backgrounds. In other words, the metric is a flat metric with an overall factor, with an overall conformal factor. We can then ask, what does this overall factor depend on? And in general, it will depend on space and time. However, because for us, only time has an invariant meaning, the spatial directions, the spatial coordinates get dualized, we will assume that the overall factor depends only on time. And if the overall factor depends only on time, then this just picks k equals 0. And so the metric we start with in our phase is just a flat FLRW metric. So this, yeah, so this takes care of the flatness problem. We can then turn to scale invariance, and in order to address scale invariance, we can introduce tau, which is the dilatation mode of the metric, and tau will be related to zeta, the curvature perturbation that we use in cosmology. And so, because we, again, because we have a topological theory, we would expect the correlation function of tau to be position independent, and in particular, it's a constant, so that this is automatically scale invariant. However, this is only scale invariant classically. At the quantum level, there is an anomaly. There is a conformal anomaly that weakly breaks this scale invariance and topological invariance as well. This anomaly is well known. It's given by the trace of the energy momentum tensor and is equal to CW squared minus AE. So, and in order to capture this anomaly, we will have an effective term in the action of the form minus tau CW squared minus AE. This is because if we scale the metric, if we do a scale transformation, it's like shifting tau, and shifting tau gives exactly this. So the difference delta S is CW squared minus AE. So this anomaly will lead to a term in the metric that is of this form. But now, because we have this term in the metric, then the 1 over lambda squared in front of W squared now starts running with scale because there is a tau here. So there's an effective coupling which runs with scale. And in fact, this sign here will give us an IR tilt, but let's do that more carefully on the next slide and see why this is in fact an IR tilt.
Can I just make a comment now, basically
Yes.
with the flatness? So Eleonora Di Valentino and Joe Silk et al. Had like some claim of 3 sigma on curvature from Planck data and maybe some other combinations. And we had a talk last week by collaborator Bharat Ratra, who's here in Korea, who basically had a 5 sigma result. So can you imagine any way that basically you could go from a non-flat phase to some sort of curved phase, like, sorry, flat phase to some sort of curved phase, if it turned out that things were, like if the observations actually preferred curvature? Like, could your model be ruled out?
Yes, it can certainly be ruled out. We cannot change, yeah, if we start exactly flat, then we will not develop a curvature. This is like setting asymptotic boundary conditions.
Okay.
But also, I think in their papers, I don't know if they use, I'm familiar with the first paper you mentioned. I think if they have BAO data included, I think they, they excluded one data set, which if they had included it, they would not have gotten the result that they had.
I think it's BAO that basically brings them back.
Yeah, exactly. So if they included BAO data, then their universe wouldn't be curved either. Right. Yeah, thank you for the question. Okay, good. So now we have a coupling in front of W squared, which is 1 over lambda squared, but now this coupling runs with scale because we have a coupling between tau and W squared. All right, so let's see now how this running gives a tilt in cosmology. In order to estimate the tilt, we can look at the 2-point function of tau and act on it with the dilatation operator. This is the equivalent of inserting the trace of the energy momentum tensor in the correlation function. And moreover, we estimate this by the disconnected piece. So as an estimate for this, we take the disconnected piece. But now we can ask, what is the expectation value of W squared and the expectation value of E? And in a weakly coupled theory, the expectation value of E receives contributions from non-perturbative instanton-like effects. So it's suppressed exponentially. So this term is, the expectation value of E is much smaller than the expectation value of W squared, which is order lambda squared. So in addition, we'll ignore this term in favor of W squared. And so what we get is a differential equation for the 2-point function, where on the right-hand side, we have a factor C lambda squared over 16 pi squared. So now we can then move to momentum space and calculate what this means for the tilt. And we get a tilt ns minus 1, which is minus C lambda squared over 16 pi squared. Now, this is a red tilt. This quantity is negative, and it is negative precisely because C is positive. And the positivity of C is a consequence of unitarity. So red tilt here is required by unitarity. Okay. So now that we have an estimate of the tilt, we can ask, can we get an estimate for the magnitude, for the amplitude of the 2-point function? And we can do that as follows. So we can complete S anomaly that we had before, so that the variation of S anomaly is exactly the trace of the energy momentum tensor. This is the piece that we saw before, and we said that the variation of tau gives the trace of the energy momentum tensor. However, we need to add these terms to cancel the variation of CW squared minus AE. And then the action that we get, S anomaly, so this is a universal action and it's complete. There are no more terms here. And this was actually derived a while ago by Fratkin and Zeitlin and was used in 2011 by Komorgatsky and Schumer in their proof of the A theorem. But in this action, we can identify the exponent of tau with capital phi. So this is the field that was in Witten's theory. This is the additional sector field that was in Witten's theory. And the equation of motion for phi being a massless field, this equation of motion gives a relation of the form box tau equals d tau squared. So now this relation and this action, they give an effective kinetic term of the form A box tau squared. So the overall factor A, and then you get some effective kinetic term that's box tau squared. So that the 2-point function for tau is a scale invariant 2-point function, and its amplitude is 1 over A. Okay, so now then we have an estimate for the amplitude and we have an estimate for the tilt, and we can ask what do these mean when put in the context of observations? So what do observations tell us about the parameters of our model? And just like we saw, so the constraint on the amplitude of scalar fluctuations lead to a value of A that is about 10 to the 10, because the amplitude is 10 to the minus 10 of the amplitude of scalar fluctuations is about 10 to the minus 10. And moreover, we expect A and C to be of the same order, so that the tilt ns minus 1, which is minus c lambda squared over 16 pi squared, will give us a value for lambda that is 10 to the minus 5. So in conclusion, the theory we're dealing with has a very large central charge, and it also is at very, very weak coupling. So it's a weakly coupled theory. But using S anomaly, we can go beyond the 2-point function and estimate higher and estimate contributions to higher point functions. These higher point functions will be non-Gaussianities from the point of view of cosmological observables. And one important thing to mention here is that these non-Gaussianities are not suppressed by small parameters like lambda or 1 over A, as opposed to inflation. So in particular, FNL is expected to be order 1. However, in our model, in the model that we take, it turns out that FNL actually accidentally vanishes. So the 3-point function actually vanishes, but it's not just the 3-point function that's order 1. All higher point functions are also expected to be of order 1. And while the 3-point function vanishes, the 4-point function does not. And we can indeed, again, using S anomaly, we can get an estimate for the 4-point function. And we do get a 4-point function, and indeed tau NL and GNL are both order 1, and there's some shape function that may be of interest for futuristic experiments. Okay, so that's non-Gaussianity. So let me now turn to a quick comparison with inflation. So both scenarios, inflation and the topological scenario, they both alter the universe at very early times only, whereas the late universe is expected to be described by an FLRW cosmology as usual. In inflation, we have a period of accelerated expansion followed by reheating. And the details of reheating are mostly unknown, but they're not important for the predictions of inflation. The predictions of inflation mostly come from the accelerated expansion in this phase, whereas the details of reheating don't add much to the story. In the topological scenario, we start with a topological theory, and then there is some type of matter conversion. And unfortunately, we don't know much about this matter conversion, but we hope that just like the details of reheating don't contribute much to the general features, the details of the matter conversion also don't contribute much to the general features. And mostly the general features are dictated by the topological phase, just like the general predictions of inflation are dictated by the exponential expansion here. And then this is a table that compares the two scenarios side by side. So and how they resolve various aspects of cosmology. So for instance, when it comes to homogeneity, isotropy, and flatness, inflation solves these problems by having an exponential expansion, which basically magnifies a very tiny patch into the size of the observable universe. For us, we saw that homogeneity and isotropy are because the problems of homogeneity and isotropy are solved because topological theories don't actually pick up positions, so that the initial conditions are homogeneous and isotropic, so they don't pick up positions or directions. So you start with something homogeneous and isotropic. And in addition, we saw that flatness is also resolved because of the condition W equals 0, so that the background is conformally flat. In inflation, we have a scale invariance, again, because of the exponential expansion. So the de Sitter background looks similar at all times, and so you get something that's scale invariant. And it's nearly scale invariant because this is not an exact de Sitter, it's a quasi de Sitter, where the Hubble parameter decreases slowly. And the topological phase, topological theories are scale invariant, and so we expected scale invariant correlation functions. And they're nearly scale invariant because this scale invariance is weakly broken by the conformal anomaly. So it's weakly broken by a quantum effect. In inflation, we get a red tilt, and this is because of the decreasing Hubble parameter during this exponential expansion. In the topological scenario, we also get a red tilt, but this is because of the positivity of the conformal anomaly coefficient C, and this positivity itself is due to unitarity. We know that in inflation, in the simplest models, non-Gaussianities are suppressed by slow parameters, so epsilon, eta, and so on. However, for the topological scenario, we saw that non-Gaussianities are typically order 1. We don't have a universal contribution to the 3-point function, but 4-point functions and higher are expected to be order 1. There may be other contributions that we don't know about, but yeah. And finally, we come to the point of tensor modes, which I haven't mentioned previously. So in inflation, we expect tensor modes to be present because there is a graviton, there's a massless graviton, and so this is a spin 2 mode that will imprint on the cosmology. But in topological theories, we don't have the graviton is absent. Our graviton, as we said, is not dynamical, so we don't have a spin 2 mode, and so we don't expect to see tensor modes in observables. So this is another way in which this can be this scenario can be falsified. If we find tensor modes, then it is not. Then it's not a topological theory. So this. Okay, so I guess I haven't mentioned this last point much, but let me elaborate on it slightly further using an analogy with particle physics. So in here, I will compare QCD and the linear sigma model with topological gravity and inflation. And I guess in QCD, we know QCD is strongly coupled at low energy, so that if this is the energy scale, at some energy below lambda QCD is strongly coupled. And it has, if you in addition consider 2 quark flavors, then it will have SU2 cross SU2 flavor symmetry. This is a global symmetry. But at low energies, QCD will form a Q bar Q condensate, which will break this SU2 cross SU2 and will give us pions. The important point, however, is that because QCD is confined at low energy, we don't have spin 1 gauge bosons that carry the QCD. We don't have spin 1 gauge bosons of SU3, for instance, at low energy. But suppose we don't want to allow our theory to be strongly coupled, then we can turn to a similar model, which is the linear sigma model. And instead of allowing the theory to go to lower energy where it's strongly coupled, we Higgs the theory first, so that SU3 breaks to U1 times U1. And now this theory is weakly coupled throughout, and we have a weakly coupled description throughout. However, there's a price to pay for this, and it is that the low energy will always have massless spin 1 gauge bosons, which are the gauge bosons of this U1, of these two U1s. The spectrum of pions can still be the same because the spectrum of pions only depends on the symmetry breaking pattern of the global symmetry SU2 cross SU2. In cosmology, we can draw a very similar picture. The energy axis now becomes a time axis where early times are, this is the early universe. And so if we extrapolate back in time, we would expect gravity to become strongly coupled. And this is our topological scenario. And just like UCD, we don't expect a graviton or a spin 2 mode, a massless spin 2 mode here. However, in inflation, we can avoid this strong coupling regime by inflating before we get to strong coupling. But just like in the linear sigma model, the price to pay here is that the graviton will always be present and we will always get tensor modes. The behavior of the scalar modes, however, in inflation is dictated solely by symmetry breaking patterns. And this is part of the success of the EFT of inflation, for example, which talks only about symmetry breaking patterns in inflation. So that the symmetry breaking pattern itself dictates the behavior of the scalar mode. And if we have a similar symmetry breaking pattern here, then we will get similar behavior for the scalar modes. So the scalar perturbations can be the same, even though the tensor perturbations here are absent, whereas they are present in inflation. Okay, so I guess.
So could you just confirm in the previous slide? So in your topological scenario,
yes,
the scalar mode come from this extra field phi. Is it correct?
Yes, that's correct.
Yeah, thank you.
Okay, so let me end here with some future directions. So this scenario is still pretty new, and there's a lot more to do. And here for us, we just considered one example of the topological phase that is based on Witten's 4D topological gravity, but there may be other realizations of topological gravity in 4D that we don't know about, and so it would be interesting to find them and figure out what their predictions are. So in addition here, we did some estimates about but for the 2-point function, 3-point functions, and so on. But it would be good to have a deeper understanding of the relation between the conformal anomaly and the breaking of topological invariance. So this part can certainly be made more rigorous. And finally, non-Gaussianities are a target for many future experiments. And here we did get a universal contribution to the 4-point amplitude and higher, but there may be other contributions that are not captured by S anomaly, and so it would be good to develop tools to systematically compute them, since non-Gaussianities again are a target, and there are many experiments that are actively looking for them. Right, so I will end with this. Thank you for listening, for your attention. And
Georges, thank you very much. Cumrun, thank you very much. I guess we're open for questions or comments.
Can I ask a question?
Yep, go away.
We speculate that in string theory, when string theory becomes very hot, there may be a phase transition like Hodgson transition or so on, after which it may happen that strings can break up and winding number may not be a real good quantum number. Would that affect any of the pictures you presented?
No, because we are not assuming T-duality.
So the existence of light tower, the details doesn't really affect your topological picture.
No, that's all we are assuming, that there's a dual description. You see, the main point is that the existence of a dual description kind of says that you cannot expect a complete description like our standard model coupled to gravity, maybe more fields. And so usually that's viewed as the good feature to have a complete description of the theory. What is funny is that string theory tells you that that's a shortcoming, not a benefit. In other words, it says that if you try to have a complete description, that means you're missing something. It should not be like that. You should have a dual description somewhere. So So that's why that's why even the puzzles exist for the regular cosmology. The regular cosmology tries to fit all the early data of the universe into one framework, and then it's difficult. And then you have to do this inflation or this crazy thing and other. So that becomes a little contrived. The whole point in string theory is that that is not natural. You expect the dual theory to come in. So what appears like a cheating resolution is actually what string theory wants to do. String theory wants to have a dual description, which is not our description. And that that's an unavoidable feature, it seems.
Yeah, sure, that I clearly see that, and which I think is quite natural, but was a bit concerned connected to my previous questions on whether this topological sector is forbidden to couple to other light stuffs or not. I mean,
well, whether it's are different, in some sense, it's like in a different universe. There's zero modes do couple. You see, there's zero modes do couple. So, for example, in the string gas cosmology, the radius in one frame is L, the other one is 1 over L. So when you change one, the other one changes. So there's zero modes do talk. So there's not, it's not like it doesn't couple at all. It's that sense of coupling. But the main point is that there should be no, whatever that coupling is, it should disappear in the X dependences. There is no X dependence in the description because they are heavy. The X modes are very heavy modes, and therefore it should be some topological theory. We don't know what it is. So as you anticipate that the topological gravity should be viewed as an effective theory in that phase. But that's only for describing our positions. There's another subsector which is going on, which is interesting, like X tilde variables and all that, which we're not describing, which is certainly very interesting for in its own right. And just we're just not describing that sector because it's not the variables that we measure today.
So they're not coupling to the gravitational variable for the entire evolution of the universe, or at some transition point that gives an effect?
Well, there would be a transition from those modes disappear and they convert to our modes. So there's an energy conservation. In other words, let me say better. Time variable is common to both variables, to both universes.
So wouldn't it be important at some stage to know how they are converted to our late time degrees of freedom? And
it wasn't crucial in our scenario, similar to inflation, where in reheating the details is not crucial typically. Yeah, so this is like that, but of course, if you want to get exact details and so on, you may get more and more questions like that you have to answer.
Thank you.
So can I ask you a question about the energy scale? It could be a Planck mass or electroweak scale. The
energy scale for the conversion.
Yeah.
Well, we wouldn't, a priori, we do not know. That's a good question. In some sense, everything we're doing, it seems to have some parallel in inflation, like high scale, low scale inflation, and so on. So these are similar in that sense. So even though there are many similarities in terms of the basic general scenario, there are sharp contrasts, as George has described, for example, the tensor modes. So, and the fact that we don't have suppression for Gaussian, non-Gaussianities in terms of epsilon suppression. So it's interesting to see that there are some common features, which is why, in our perspective, why inflation is phenomenologically successful. Why does it even work? And so this is because the fact that inflation takes a point and blows it up to an infinite size or to an observable universe, which is why there's no X dependence, because that whole one point is basically all the universe. And that's why the topological feature is equivalent to that same statement. So in some sense, the different ways of getting at the same thing. So that's why there's some commonalities between them.
Okay, any more questions or comments?
Okay, I think I raised my hand, but maybe I can talk. I have one question and also one comment about this alternative model. What is the way to basically rule it out? Okay, so there is no tensor mode, which is understandable. If we find some substantial amount of tensor to scalar ratio like R, then okay, the model can be ruled out. But then if we don't find it, again, we have inflationary scenarios that R can be very small. And within the observational limits, we cannot really rule them, compare these two models. And then I think it was talked about the non-Gaussianity of the 4-point correlation function. But again, finding non-Gaussianity at the 4-point correlation function is something observationally very difficult.
Correct.
So yeah, how to rule out this model?
Well, so you're asking a practical question, but I think but conceptually you just explained why the big differences are. So a 4-point function prediction for non-Gaussianity is very non-trivial. And it may be that, in our, in the next few years, we won't be able to put our hands on it. But to say that's impossible experimentally is a bit unwarranted, perhaps. It is possible that at some point we'll get our hands on those. So that could be a way to assess these. The tensor mode also, even though my understanding from inflationary models is that tensor mode is, even though it can be avoided, it's not natural to avoid. So in other words, just a few of these things, if you get a few of these things lining up with our model, it makes our model more natural than inflation. So of course, the same question could be raised to inflation. How can you rule out inflation? It's very difficult.
No,
So,
I certainly agree that, you know, inflation suffers the same thing, that, you know, it's
but
almost
I think that
impossible to rule it out.
our model suffers less than inflation in the sense that we have no way out. So we have, in other words, it's hard to find ways to rule out inflation. Whereas we are giving you a way to rule this out. Tensor mode will rule this out.
Yes, fair enough.
Yeah.
Okay, and one comment about the discussion about the flatness. I would like to say that, okay, maybe the conclusion was correct that when we add BAO and CMB, things back to the flat, but that's not a right argument, I would say, because there is some weird tensions. I mean, there might be a problem with the data or with the model. So, but one can get to the flatness from other perspective by comparing the low redshift data together, like a BAO and supernova, which shows that yes, flatness is consistent. But what is happening with the CMB is something weird going on, so one has to find out. But yeah, combining with BAO and saying that, okay, everything is consistent with the flatness, I think that's not a really correct argument to support flatness.
Yeah, actually, Armin, we had a speaker last week who was claiming 5 sigma, basically. So they have a slightly different power spectrum. They assume a different power spectrum for Planck. It's not a tilted one. And this is, what's the name of the chap's name? Changu Park. Basically, he's a collaborator of Bharat Ratra.
I'm sorry, I don't buy that. I mean, you know.
You know, of course, I don't think anybody buys it, but
yeah, I mean, if people do proper analysis and proper statistical analysis, things are not like that. Certainly, yeah.
It's certainly a hot topic, very interesting and hot topic, right? Okay. Any more questions or comments?
I think so I think I do have a comment about non-Gaussianities of the 4-point function. There are some proposals for, I don't know if there's an experimental proposal, but people have argued that you can find tau NL order 1 or something if one can measure anisotropies, correlations between temperature anisotropies and then spectral distortions in the CMB. So if it's like the T-mu correlations or something is what they called it. So yeah, I think it might still be futuristic, as you say, but getting to order 1 in principle is not impossible for the 4-point function.
Okay, thanks.
Yep.
Questions or comments? Any further ones? Actually, Cumrun, can I ask a little bit about the motivation? Cumrun?
Yes.
So basically, you just mentioned the distance conjecture, but you didn't discuss the de Sitter conjecture or the trans-Planckian censorship conjecture. But I mean, of course, probably this is there in motivation in the background. Is there a reason you downplayed them, or?
No. Those are to downplay why inflation and all those models are not natural. So the aim of the talk was not to shoot down other models, more to explain what our model is.
Okay.
So of course, the motivation to look for other models would be the swampland conditions, which I did mention.
Yeah.
But yeah, no, I mean that is certainly, to me, inflation is unnatural for many reasons, and one of them is these very flat potentials, very unnatural, and not only just unnatural, they seem inconsistent in some ways. Now we cannot say they have completely been ruled out, but if you take TCC, they're essentially ruled out. So there is this tension with inflation, which is the question then is, okay, what do you replace inflation with? This is a proposal of what it is that will replace that early phase of the universe with.
Question?
Yes?
Yeah, go.
Okay. Yeah. So I have a question about the scalar power spectrum and the usual inflationary picture, even though we have not tensor mode in the linear level, but if we consider higher perturbation, we can have induced tensor mode. But you are saying that even that tensor mode does not exist from the topological vision?
Oh, I see. That's a good question. So in inflation, that tensor mode is very small, right? It's like 10 to the minus, like R is 10 to the minus 5. I don't remember the exact number, but it's very tiny. But I think we probably might have something similar too. But it will be, yeah, I see. Yeah, that's a good question.
But technically, so you computed the 4-point function, for example, then that could induce the tensor mode. That's a usual story in inflation. So that's the point that I'm worrying. So I mean, if you are
Right.
considering topological theory, I guess even that mode would not be allowed.
Right. No, but I think yeah, I guess so I haven't checked this very carefully, I think, but I mean, if it's present or not, then if you can measure the 4-point function, then you can also compare and see if the tensor mode you see can be sourced by the 4-point function that you also see. So if you can measure both, then I think there's no ambiguity.
But the tensor mode in inflation is driven by graviton fluctuations. My understanding is so we don't have that mode here.
No, I'm saying that even though at the linear level there is no tensor mode, but if you consider higher,
but you're saying if there could be some suppressed leftover piece. That's if I understand you. So suppressed leftover piece we could study to see if there's a piece. I mean, it's a higher order term that we have ignored or what, but certainly it's not at par with the inflation. Inflation expects much stronger, unless you contrive your inflation models.
Okay, I think it's a good question, Moen. Good question.
Okay, thank you.
Any more questions or comments? Stephen? No. Hisayoshi? No. If not, then I think we can thank our speakers again. Okay, for a very interesting talk.
Thank you for inviting us.
Thank you very much.
Thank you.